So we're back. Hopefully you were understanding what we were doing on the drill there. And I'm curious how you did the second one on the drill, because I did it with trial and error. I'm sure there are other ways you could come up with an answer. So, hey, I'm just curious what you got. So our objective today is that students will learn that, oh, by the way, this is not your homework. Your homework is what's on its learning. Okay, so today we're going to learn the fundamental theorem of algebra, which I know seems weird that we're learning that in trig, because you would think you would learn the fundamental theorem of algebra in algebra, but we're going to learn the fundamental theorem of algebra in trig. And we're going to learn some other factoring techniques in order to solve polynomial equations. So some of the stuff we're going to do after the polynomial, some of the practice stuff, is going to be factoring problems. So like there'll be like probably 4 or 5 factoring things that you need to do, and then you'll be able to go on and then come back and look at how we're factoring on this. So we're just doing this one lesson today, or this one lesson this week, 7.6 and 7.7. And we're going to start with 7.7 first, and then we'll go back and do 7.6. 7.6 is the factoring, and 7.7 is the fundamental theorem of algebra. I may have that backwards, but you know what? It doesn't matter, because most of you probably don't have your books. I'm just throwing them out there. So what we're going to look at first of all are some polynomials theorems. So some theorems about polynomials. First off, the fundamental theorem of algebra is that every polynomial has at least one complex zero. Every polynomial has at least one complex zero. So here's the deal. Remember we talked earlier and we said that complex numbers, all real numbers, are a subset of the complex numbers. True? So that's telling me that if I have a solution and it's real, it's also complex. Okay? But if I have a parabola that opens up, and that parabola that's opening up doesn't intersect my x-axis at all, that means I have a complex solution. I have a solution, it's just imaginary, it's just complex. So that's one of the things we have to keep in mind of here. So for instance, if we have the graph of a line, okay, so if we drew our x and y axis on here, can't really do that in black, so here's my y-axis, here's my x-axis, you can see that indeed we do have a solution right here, right? And that's, even though it's a real solution, because the real numbers are part of the complex numbers, that's also a complex solution. Likewise, if we had a parabola quadratic equation that did something like this, and it appears as though there are no solutions, there are no real solutions. There are complex solutions. They're just not going to be real. So you would solve this using the quadratic formula, or maybe you might factor out some stuff and see if you can get it smaller depending on what the quadratic does. And then you could have something where your graph does a little something like this. Okay, and so that's a degree that it could be degree 2, it could be degree 4. And so some of our solutions are real, but we also have some that are complex. So you could have a mixture. But each and every one of these has a complex zero. Okay? So let's erase all of this stuff. And let's move on to the next. I'm sure I probably could have put the thing that says erase all ink. Hey, that was pretty funny. That guy's name was Crispy Bacon, wasn't it? That was good. I like it. So our next theorem says a polynomial of degree n has at most n zeros. So in other words, whatever our degree is, that's the biggest number of zeros there could be. So if it's degree 4 and it has 5 zeros, you did something wrong. If it's degree 4 and you found 2 real zeros, that's okay. There could be 2 real zeros. They could be double roots. There could be 2 complex zeros. But what happens is you have to take into consideration what the degree is. It can't have more solutions than it has degrees. So if it's degree 5, it can have up to 5 unique solutions. The number of zeros theorem says, a polynomial of degree n has exactly n zeros if multiplicities are counted. So you're saying to yourself, she just said that it could have at most n zeros. It's true. What this theorem says is, whatever the degree is, that's how many zeros you have. But it says you have to count multiplicities. So for instance, let me go to Desmos. Okay? So in Desmos, I'm just going to type in an equation. And I'm going to type in the equation x plus 2, x plus 3 squared. Okay? Now, when you look at this graph, how many solutions do you see? Good, good. You only see one, and that solution is -3. But this expression, if I FOILed it, if I multiplied it out, y equals x squared, keep it in control, squared, plus 6x plus 9. Okay, so they're the same. All right? So if I had graphed this, it would look like there's only one solution, right? But there's actually 2 solutions here. Why? Because the factors of this are x plus 3 squared. So that means when I solved this equation, if I go back to my flip chart, and I had the equation which said x squared plus 6x plus 9, which equals x plus 3 squared, and I want to know when that equals 0. So that means that x plus 3 equals 0, and x plus 3 equals 0. Well, how many factors are there? Well, there's 2 factors. So there's 2 solutions of -3. We don't write them twice because we're not idiots. We're like, hey, we work smarter, not harder. Not that writing it twice makes you an idiot. But work smarter, not harder, so you don't have to write them both twice. You would just say that x equals -3 is our solution, and that's a double root. So you would put a dr, because it counts as 2. So that would mean that this polynomial of degree 2 has 2 solutions. Okay? Okay, so we're back, and our next theorem says a graph of a polynomial degree n can cross any horizontal line at most n times. So if you remember earlier, I had freehanded that one graph, and I had said, okay, so here's my x-axis, here's my y-axis, and I had sketched a graph, and it did a little something like this, right? And I said, well, this could be degree 2, it could be degree 3, it could be degree 4. How do I know which one it is? Well, I don't, because the way it is now, this is looks like degree 2, right? Because it has 2 real solutions. But when I look over here, now I see I have 1 real solution, or maybe that's a double root. So here I have 2 solutions. Up here it looks like there's 3 solutions. Up here it looks like there's 4 solutions. Here it looks like there's 3 solutions again. So what's the largest number of solutions there could be? Well, there could be 4. Because we're looking at where does this cross the x-axis. Well, if we had the x-axis up here, it'd cross once, twice, 3, 4 times a lady. And so that would be our solution. But our original equation, originally this started out down here. So what we're saying is when you have a graph, you want to take your pencil and see how many places it can intersect. So if it can cross n times, then it could be degree 4. If it could cross 6 times, it could be degree 6. However many times it could cross through that x-axis. And I think this might be our last theorem. Yes. Our last theorem is one that I thought we already did, but we didn't. So it says if a plus bi is a 0, then the conjugate is also a 0. So what does that mean? Well, that means if we have a solution and we've solved using the quadratic formula and we found that 3 plus 4i is a solution, guess what? So is 3 minus 4i. Because if you recall, when you solve the quadratic formula, it's x equals opposite b plus or minus the square root. See that plus or minus there? Tells you that it's 1 when you add and 1 when you subtract. And that's why if you get a plus bi, a minus bi is also a conjugate. It's also a solution. So we're going to try a couple of these properties, okay? Okay, so what we have here are three similar yet different quadratic equations. You want to the first equation is f of x equals x squared minus 6x plus 8. And you can see this is graphing, crosses the x-axis two places. So that tells us we have two real solutions. One of those real solutions is 2, one is 4, and we know that. When we look at the next equation, we have g of x equals x to the second minus 6x plus 9, which you can see when you graph it. You have 1, 0, which is at x equals 3, which means you only have one solution. But Miss Finney, it's degree 2. You're right. It's degree 2, which means we could have at most two solutions. And remember that our fundamental theorem says that everything has to have a complex solution. So over here, even though we see that the solutions are negative or 2 and 4, we know they're really 2 plus 0i and 4 plus 0i. Here, this is probably going to be a double root. 3, because remember when we factored x plus 3 and x plus 3, we had x squared plus 6x. We factor this, it's going to be x minus 3 and x minus 3, so that's going to double root it. Here when we graph x squared minus 6x plus 10, notice all we did each time was add 1. And it just moved the graph up 1 unit. And now we have no real numbers. But what I'd like to do is show you how the quadratic formula comes into play here. So if you remember, the quadratic formula is x equals opposite b plus or minus the square root of b squared minus 4ac, all divided by 2a. We've often said that this part here, and when I taught the quadratic formula, I always taught kids to calculate that part first, because that told you whether you had to keep going or not. That part there is called the discriminant. Okay, so that tells you whether or not you're going to have what types of solutions. If your discriminant is greater than 0, then you have 2 real. If the discriminant equals 0, then you have 1 real. And if your discriminant is less than 0, then you have 0 real solutions, or 2 complex. So that's what we're looking at here. So when we look at our B, our A, and our C, so for the first equation, our B squared is 6. So we're going to have negative 6 squared, which is 36, minus 4 times 1 times 8. So 36 minus 4 times 1, 4 times 1 is 4, times 8 is 32. So 36 minus 32 is positive 4. So our sign here is positive 4. So that means we're going to have, it's greater than 2, it's greater than 0, so we're going to have 2 zeros. And those zeros are going to be 2 and 4. And that also tells us what our factors will be, because our factors will be the opposites of that. Okay? All right, so let's take a look at the next one. Now, this time, what's our discriminant? Well, our discriminant is negative 6 squared, which is 36, minus 4 times 1, which is 4, times 9, which is 36. So 36 minus 36, which is 0. So since our discriminant is 0, that means we have one solution. this one solution is at 3. And that means our factors are x minus 3 and x minus 3. So you'll see there that that's a double root. It has two solutions. It counts twice because there's two factors there. There's an x minus 3 and an x minus 3, both resulting in a positive 3 for our solution. And then finally, the last one, we've got negative 6 squared, which is 36, minus 4 times 1, which is 4, times 10, which is 40. So this time, our discriminant is negative. If our discriminant is negative, that means we have 0 real zeros. Well, how did they get 3 minus I and 3 plus I? Here's how they got 3 minus I and 3 plus I. Are you ready? They used their quadratic formula. So we said that our discriminant was negative 4, true? All right. So that means on our discriminant being negative 4, b was negative 6. So that means we have 6 plus or minus the square root of negative 4 divided by 2 times a, which is 1. Well, the square root of negative 4 is 2i. So we have 6 plus or minus 2i divided by 2. When you divide everything by 2, you've got 3 plus or minus I. 3 minus I, 3 plus I. So then your factors are x minus 3 minus I and x plus 3 minus I. I probably shouldn't have used green on blue over there. See if I can change that color. That would be better. Okay, so that tells you how we got those solutions, and that tells you what our factors will be. But I believe on here that what they did for our factors is they left them like that. Now, if we're going to multiply these together, then of course we would distribute that negative through. I'm sorry, I did that wrong. This should just be minus. Both times it's minus. Okay? So what I'm going to ask you to do is I'm going to ask you to pause the video, and we're going to meet after the pause, okay? I'm going to ask you to pause the video, and I'm going to ask you to graph these 5, okay? Sketch them on a piece of paper. Write what their zeros are, and write what the degree is. Now remember how we calculate degree. So this one is an x to the first times an x to the first, which means this is going to be degree 2. This is an x to the first, and that's an x squared, so this is going to be degree 3. So this should have 2 solutions, this should have 3 solutions, this should have 4 solutions, 5 and 6. So what I'd like for you to do is just take these 5 equations, sketch them, determine what their zeros are, and decide what they have in common and what makes them different. And we're going to come back and talk about that.